Okay, moving on from the normal distribution to asking a very important question. Um, is a data set from a normal population or a near normal population? That's important because many statistical methods that we will consider later in the course require that. Okay. Now, there's a lot of different techniques to check for the appropriateness of assuming normality. You could look at a box plot and look at the symmetry of a box plot, or look at a histogram or even a stem and leaf plot. Of those three, the histogram is probably the best for assessing normality, but a better technique than that is to use what's called a normal probability plot. The reason I say it's better, a histogram is nice in displaying the shape of the distribution of a data set, but if there's not that much data to begin with, the histogram cannot give you a good sense of the shape. So another technique that kind of gets around that is this normal probability plot, sometimes called a quantile plot or QQ plot. And the QQ plot is basically this. On the coordinate plane here, you're going to plot the data. This is one way to do it, I should say. You're going to plot the data, which is y sub I, and I put I in parentheses there, that subscript. Y sub I is the ordered, or the ith ordered data point, and on the horizontal scale you're going to plot this versus normal quantiles or normal percentiles let's see here, normal percentiles, and the notation for that is z sub 1 minus p. Okay, so what you're doing is you're plotting the data point with its corresponding normal percentile. Okay, now how do you figure out what the percentile would be under normality? The book uses the approach, this ratio here, I minus 0.375 over n plus 0.25. I'm not going to go into a lot of detail where that came from, but they use that to get a good sense of what the value of p is under normality, and so that gives them the upper pth, or the pth percentile that ties together with that ith data point. Okay, so doing this by hand, admittedly, is cumbersome. It takes a while to do. The book illustrates on how to do it by hand. For us, we're mostly going to be interested in letting a statistical package do it for us, and also evaluating just somebody else's QQ plot and their assessment of normality. But really, the big takeaway for us is this, number one here. If the QQ plot, or the normal probability plot, is approximately linear, then the normal assumption is tenable, that is, it's defendable. But if you have some strong non-linearity in your plot, that is, you want your plot to look something like this. Okay, if that's the case, then it's reasonable to assume that your data came from a normal population. If that's not the case, then you're going to have to recheck some things. In particular, what you can do is you can transform the data. That's a possibility to help achieve normality. Now, generally the eyeball test is used on the QQ plot to check for normality. JMP has an ellipse that you can check to see, or not an ellipse but a region you can check to see if there's a lot of data outside that region that might be cause for concern of lack of normality. Your text also gives an approach to looking at the correlation coefficient of this QQ plot, and that correlation coefficient can be tied to a particular test for normality. But again, we're going to mostly use JMP to construct a QQ plot and to perform a formal test for normality, which we'll look at later on. But this is an important idea, using a QQ plot to evaluate whether or not a population that you have sampled from is in fact normally distributed.